Ore operations. Frequently asked questions. Ore has innovatively combined well-established technologies, creating a practical and patentable series of systems. These systems naturally enhance their output and capacities, enabling them to generate utility-scale electricity and water. Remarkably, around 80% of the equipment used to operate these systems consists of readily available, off-the-shelf parts. The Ore system stands apart from other technologies thanks to its use of universally recognized applications. What makes it unique is its remarkable capacity to generate vast amounts of renewable power. This extraordinary power generation also comes with a substantial bonus. The system produces a significant quantity of water as a byproduct. This water condensation is a natural outcome of the air compression process. UL certification. It's crucial to understand that while individual components within the Ore system may have UL certification, the system as a whole might not necessarily be certified. Instead, each component receives certification based on its specific functions and safety standards. To ensure the overall safety and reliability of the entire system, it's imperative to adhere to the relevant safety standards and guidelines. How many cubic feet a minute and what pressure of compressed air is required for each generator? The table shows typical compressed air volumes for operating generators. The pressure can be increased. The benefit of increasing the pressure would be in the number of air motors to operate the generators. The 90 psi, or 621 kilopascals, was selected due to the availability of air motors that operate at that pressure. Generator kilowatt rating cubic feet per minute at 90 psi or 621 kilopascals. If the Ore system must come to a complete stop with no mast rotation due to unforeseen circumstances and no wind, can the facility still produce power? Yes, absolutely. The compressed air in storage tanks is used to keep the system operational. If so, how long can it produce power without mast rotation if all pressure vessels are full and no wind is available? 13 to 14 days of continuous power and water production. However, replacement or repairs should not take longer than a day or two at most. How is the reactive power compensation handled? The Ore generates electrical power for distribution outside the facility. The generators have a power factor of 80%. The phasing and regulation of the delivered power is adapted to the external use and user's application, sometimes needing transformers. Reactive power compensation is generally handled close to the load. In this case, the power is being transferred immediately outside the Ore facility to a user system connection, which in most cases would be the farthest from the load. What is the proposed compressed air storage capacity, and time in which the stored air can fully power each and all generators per unit? Compressed air storage serves multiple purposes, with minimal usage in ancillary applications like pumps and blowers. Or forced rotation systems consume a larger share, but it remains under 5% of the total. A significant portion powers generators, with a planned surplus of around 25% released into the atmosphere. Ore's compressed air storage covers uses at 90 psi or 621 kilopascals working pressure, and high-pressure bulk storage at 5,000 psi or 34 million pascals. Forced rotation. The forced rotation component system in the Ore operating systems is a valuable upgrade. It can initiate and maintain tower rotation even in low wind conditions, from 1.6 to 3.2 km per hour. It also helps with braking during maintenance when reversed. This system runs on a portion of stored compressed air delivered through low-pressure supply piping, 90 psi or 621 kilopascals. It uses an Ore air motor to transfer rotation directly to the drive shaft and stabilizes speed changes through the pneumatic transmission. Compression volume is in part dependent on wind speeds and forced rotation use. The higher the wind speeds, the greater the volume and less consumption for forced rotation. The lesser the wind speeds, the greater the amount of forced rotation used to maintain a given level of rotation and compression volume. The additional storage capacity will allow the forced rotation systems to operate at a higher level to increase the RPM and increase compression volume rates. Take the planned installation without added storage capacity. The 28,000 cubic feet or 44,000 cubic meters at 5,000 psi or 34 million pascals storage, when regulated down, brings the total 90 psi storage capacity to 1.6 million cubic feet, or 4,000 cubic meters at 90 psi or 621 kilopascals. How loud are the Ore flutter vanes as compared to a wind turbine? A turbine blade tip measuring 200 feet would be traveling at a velocity of 340 meters per second, which is equivalent to the speed of sound, while maintaining a relative speed of 10.2 meters per second. This creates something called a wave drag. The resulting shock waves at the tips are the perpetrators as to why the propellers are so loud. The oar does not use propellers to rotate. Most importantly, unlike horizontal axis wind turbine blades that are rotating against the oncoming wind, half of the rotation of the oar structure is turning with the wind. Noise is projected to be minimal, and will easily attenuate to persons on the ground within 10 to 15 meters of the facility at below an estimated 70 decibels. How much power is produced by the flutter vanes? The power produced by wind alone with the oar flutter vane is calculated by using the wind industry power of the wind formula, where the velocity is cubed. Friction and aerodynamic drag are applied to the wind speed before cubing. The horsepower needed to operate the small radial compressors used in the flutter vanes is computed using the 124 psi or 850 kilopascals compression, the volume of air being compressed and calculated by each piston at various stages in the up and down strokes.